All right. So, hi everyone. First of all, let me welcome you guys to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy where everything is being taught to you completely in English. So, this is a series that I host for class 12 students, and the topic that we are going to discuss today is electromagnetic induction. This is lecture number 5, and today we'll be talking about self-induction. Okay. So, before we start with today's lecture, let me introduce myself for those of you who might not know me yet. Okay, so my name is Rohit Dixit, and I studied mechanical engineering from IIT Delhi. And for almost 8 years, I've been teaching physics for the IIT JEE exam now. So all this teaching so far had been associated with offline institutes. So offline, I've been associated with some of the topmost institutes in the JEE field, and this is the first time that I'm teaching online. So here we are. I myself was a student who was All India rank 447 and All India rank 192 in the two stages of the IIT JEE exam that I took. I also qualified the NTC Stage 2 as a student, and I was in the top 1% in the NSCP exam also. I've already coached many students to top ranks in the IIT JEE exam, and now I hope to continue doing that here online with you guys. So, how can you guys make sure that you are also benefiting from even in this lockdown, you are going on with your preparation without any trouble? This is how you can do it. You can go get yourself the Unacademy subscription. Okay, with this subscription, you will get benefits like live classes where you get to interact with your educators on a regular basis. You also have live polls and leaderboards in these classrooms, which keep them highly interactive and fun. And you have test series and analysis sessions, which keep you completely on your toes at all times. And then you have live doubt clearing sessions. So after every 3 teaching sessions in all Unacademy courses, the fourth session is supposed to be a live doubt clearing session. So make sure you're getting your Unacademy subscription and making the best of all your courses. So on top of all these benefits, you're also getting a chance to study from India's best educators uh, from the comfort and safety of your home. All right. So these are the ongoing courses on the Unacademy Plus. Okay, so which you can enroll in with the help of your Unacademy subscriptions. Okay, we'll just wait for it. Yeah, so as I was saying, okay, so here are the courses that you can join. All right, I for education. How are you? All right, yes. So here we go. These are the ongoing plus courses of our JEE Mains and Advanced 2022. So there are 3 courses which are being taken by the JEE English team. So these include 2 courses by Abhinav sir and Rahul Kaushik sir, and I myself am taking an advanced course on mechanics. So these are the courses, 3 courses meant for class 11 students or 2022 aspirants. Even 2021 aspirants can join these courses if they want to get master those topics. All right. Similarly, you have another 4 courses which are ongoing for the IIT JEE Mains and Advanced 2021, including an advanced course in electromagnetism that I am taking. All right, so hurry up and join these courses as soon as possible. How can you do that? Very simple. So first, you need to install the Unacademy app. Good evening, Rajesh Chandra. How are you? And hello for education. Okay, sure. Yeah, I have been busy with the holidays. Okay, so all right for education. So as I was saying, so how do you enroll in these courses? Very simple. First, you need to install the Unacademy app. Or once you've done that, you will need to go to the plus section of your app. Then select your goal as IIT and then click on that Get Subscription button. Now, when you click on that Get Subscription button, you'll be redirected to the payment page where you can use the code RD Live as in a box where it will say, "Do you have a code?" Okay, and you will already realize that the fees have been kept very competitive. So any reputed or offline coaching would charge you anywhere between 4 times to 8 times this fees. And so Unacademy is providing you the same quality education from the same top educators at a very affordable price, which will be made even more attractive if you use this code RD Live. Get another 10% off. And also, when you click on proceed to pay, you will realize that you have no cost EMI options which are available for 6 months subscriptions and above. So to make it easy for you to get the subscription, all right. So at these prices, trust me, this subscription will be definitely worth having. It will definitely give your JEE preparation a lot of boost. As you can see, the 24-month subscription comes at about 2,300 rupees per month, and the 12-month subscription comes to about 3,200 rupees per month pricing. So, which is definitely very affordable and completely worth it. All right, make sure you're getting your subscriptions as fast as possible. So, hi Meet, how are you? No, I haven't made my own channel, Meet. This is the only channel where you will find me. Okay. Also, the Unacademy Combat is going to be live on this 22nd of November. This is the most competitive gamified IIT JEE battle, and you can enroll in these. And if you do well, you can win rewards and prizes. So make sure you're enrolling in them as soon as possible, and you can use the code RD Live to register for the uh, Unacademy Combat. Okay. All right. So moving forward, those of you following us on the JEE English channel of YouTube can connect with us on the Telegram app using this link, so that you are getting all the notifications of all the sessions and lectures happening on the JEE English channel. Okay. Okay. There will be more subscribers than here. Okay. Hello, Chetan. Oh, okay. Thank you, Meet. Thank you, Meet. I haven't thought about it yet. Maybe in future sometime. Maybe I will do it. All right. Anyhow, so why don't we get started with today's topic then? So this is lecture number 5 of electromagnetic induction, and today we'll be talking about self-induction. Okay, so first of all, let's try and understand what self-induction is. So as you can see, here in this figure, you have a coil from which the current is passing, and if the current is passing, this coil obviously creates a magnetic field, and the flux due to that magnetic field is passing through this coil. It's linked to this coil. So what will happen if the current through this coil starts to change? You will realize that will cause a change in the magnetic field that is being caused, which in turn obviously creates a change in the flux linked with the coil. And from Faraday's law, we know that wherever that happens, there is an EMF that gets induced in the coil. So that is what self-induction is. So let's talk about it in a slight detail now. So the property of self-inductance is a particular form of electromagnetism. It is not a new phenomena. It is just a form of electromagnetic induction only, which we have been studying so far. Okay. So it is defined as the induction of voltage in a current carrying wire when the current in the wire itself is changing. So that is why it is called self-inductance. This gets induced due to the change in current of the wire's own current. Okay. So its own flux starts to change. Okay, sure, me. Of course, of course. Okay. So this induced voltage created by the changing current has the effect of opposing the change in current. So you already know that that is what Lenz's law says. Lenz's law says so any change in flux will induce an EMF which will try to oppose the change in flux. So whenever current is changing, so if the current was increasing, you realize the flux would have increased. So the induced EMF would have tried to oppose an increase in current. So it would have tried to reduce the current. If the current was decreasing, then you would have realized that the flux would have decreased. And in that case, to oppose that change in flux, the EMF induced would have tried to increase the change. So that is why this is called back EMF. Okay, it will act opposite to the external EMF, which is causing the change in the current. Okay. Okay. So similarly, you know that if in a coil or a conductor, the current I is flowing, then you will realize that the magnetic flux phi will be linked to the same coil will be directly proportional to the current. Okay, so I hope you remember, even for a solenoid, V was mu naught n I, or for that matter, any due to any current carrying element also. If you realize, your dB vector was given as mu naught over 4 pi times I times dl cross r over r cube, right? So you realize, in any current carrying segment, the magnetic field produced is always directly proportional to the current. Okay. So since the magnetic field produced is directly proportional to the current, so the flux linked to the coil will also be directly proportional to the current. So I can write that the flux phi, magnetic flux, is directly proportional to the current. Now, if I introduce a proportionality constant, then that is what is called the coefficient of self-induction. So if I remove the proportionality constant, I write that the flux linked with the coil would be directly proportional to I, or some constant times I. That constant is called the coefficient of self-induction. Okay. All right. So moving forward, now we will talk about a new circuit element which is called an inductor. So far we have studied two circuit elements. One was resistor, one was capacitor. So both had their own roles. So the role of the resistor was to actually draw power from a circuit and dissipate that power or use that power in some way. Okay. Similarly, you studied about a capacitor. Capacitor was a device which was used to store energy in form of electric field. Similarly, an inductor, which is also called a coil or a choke. So you must have heard these names also. So these are two alternate names for inductors. Okay, so an inductor is an electrical component that stores energy in form of magnetic fields when electric current flows through it. So just like when you charge a charged capacitor stores energy in form of electrical fields. What this does is, an inductor, when you will realize, when current is passing through an inductor, it creates a magnetic field. Now, just like electric fields, these magnetic fields also store energy. So this is another device which can store energy and later be used whenever we have a requirement for energy. Okay, so an inductor typically consists of an insulated wire wound into a coil, as you can see, just like a solenoid. A solenoid is an example of an inductor. So an inductor is characterized by its inductance. So whenever we talk about a resistor, we talk about resistance. Whenever we talk about capacitor, we talk about capacitance. So similarly, whenever we talk about an inductor, we define something called an inductance. And inductance is nothing but another name for the coefficient of self-inductance that we had studied here. Okay, this is what you call inductance. You can also call it coefficient of self-inductance or simply inductance. Okay. Now, in an inductor, this inductance is defined as the ratio of voltage of a rate of change of current, or voltage to the rate of change of current. So this is also very, very simple. Okay, you know that since flux passing through the inductor is equal to L times I, so you will also realize the induced EMF or the back EMF would be ratio of the voltage induced. By the way, this would be voltage induced. So whatever voltage is induced to the rate of change of current. So you will realize the induced EMF would be nothing but L times di over dt. That is what it is saying, or rather with a minus sign because of Lenz's law. So from here you can say that L equals minus times induced EMF over di by dt. That is what your definition says. Okay. So the inductor is characterized by its inductance, as I said. Okay, which is the ratio of voltage to change in rate of change of current, and the SI units of this are inductance are Henry. Okay, so again we have given that name in the honor of a great scientist who had independently discovered the phenomena of electromagnetic induction. By the way, so one, you already know that Faraday did some work, and Henry was another scientist who had done work on electromagnetic induction. So to give his work recognition, we name the unit of inductance as Henry. So let's talk a bit more about inductors and inductance. So inductors can be divided into two categories. So one, an ideal inductor. What is an ideal inductor? An ideal inductor is an inductor which can be assumed to be made of an ideal resistorless wire. So as I said, an inductor is nothing but a coil of wire wound like this. So that coil practically will have a resistance. But when we talk about an ideal inductor, we talk about a coil which is completely resistanceless, so it only has an inductance and it has no resistance. So that is what we will be treating most of our inductors as. And the circuit symbol of an inductor is this. So that's it. This is the circuit symbol of an inductor. Okay. So nothing new here. So make the sign of a solenoid. That's about it. Okay, and then you have real inductors, which are obviously any inductor which is made up of a conducting coil would have some resistance. So a real inductor are ones which have a resistance in the coil. So these are characterized by both inductance and resistance. So whenever you are writing about an ideal inductor, then you only specify its inductance. So you will only talk about its L. For any real inductor, however, you will talk about its inductance plus its resistance. Okay? So L comma R, this is how you represent it. And a real inductor can be in fact considered to be a combination of an ideal inductor and a resistor, just like your real batteries. Okay, real batteries were considered to be a series combination of an ideal battery and a resistor. So similarly, this can be considered to be equal to an ideal inductor and a resistor combined in series. Okay, so this is what an ideal real inductor looks like. Okay, this is how we will treat real inductors. So we will talk about that in further detail when we move to that discussion. So hello Divya M, good evening to you too. How are you? Now inductance obviously is a scalar quantity. Why? It was also defined uh, as I said, phi was defined as L times I. So you can also define L as phi over I. Okay, or the flux linked to the inductor per unit current. Okay, so current is a scalar, flux is a scalar, so ratio would obviously be a scalar quantity. Okay, now the inductance obviously depends on the shape and size of the inductor. Sometimes also you use a magnetic core to increase its inductance. So that is when it would depend on the material also used in the core. Okay. Next, let's try and calculate. Let's try and calculate the inductance of a solenoid. So how do I calculate that? Let's see. So I know how you define the inductance. You know that inductance is defined as phi over I. So if I can calculate phi, then I can immediately know what the inductance is. So let's try and calculate the phi. So when a current I is flowing through a solenoid, assuming that the solenoid is infinite. So assuming the solenoid to be infinite. So how do I do that? Obviously, you have to take the length of the solenoid to be very, very large compared to its other dimensions. Okay. So if you do that, then you can assume your solenoid to be infinite. Then you know that what is the magnetic field that it produces? It produces a magnetic field of mu naught Ni. I hope you remember this formula. Mu naught was the magnetic permeability of free space. N was number of turns per unit length, and your I was the current. Okay. So I hope you remember that. Now you will know that phi is capital N times P times A. So where capital N is the total number of turns. Okay, so I can write this as small n times L, where L is considered to be the length of the solenoid, and imagine it has a radius of R. Okay, so I'm imagining that the radius is R and the length is L. The length, though practically finite, is very large compared to the radius. That is why we are using the formula of infinite solenoid. So you will realize capital N will become N times L. And then for B, you already have mu naught Ni. And how about area? Area would have been pi small r square. So you realize phi, or the flux linked with the inductor, comes out to be mu naught n square I times pi r square L. Okay, I hope you can see that. Now you will realize from here that L would be phi over I, which is nothing but mu naught n square pi r square L. So you realize, as I had said, this depends on the dimensions and the shape and size of the coil. So this, you realize that the inductance of this solenoid is depending on what all? Let's take a look. So it depends on the number of turns per unit length. It depends on the radius. It depends on the length. Now, sometimes we also talk about inductance per unit volume also. If you wanted to talk about that, then that would simply be mu naught n square. Okay. Inductance per unit volume of the solenoid would be, why? Because this is the volume. I hope you can see that. The volume of the solenoid would be this. This is volume of solenoid. Okay. So L over V, which is the inductance per unit volume of the solenoid, would be mu naught times n square. Okay. This is a formula that you can remember also, very easy to remember formula, nothing too complicated about it. So remember, this is going to be our approach if we are to find the inductance. Okay, we will always try to find the flux corresponding to any current and then divide that flux with the current. That is how we will get the expression for the inductance of any shape. Now, usually you may be asked to calculate this or you may be given the value. Most of the times in questions, you are given the values of inductances, so you won't have to worry about calculating these. Okay, but you should still know how to calculate this. All right, so why don't we have a practice problem? So let's try a slightly complicated problem. Okay, so in this problem, you've been told to calculate the inductance of a toroid whose inner radius is equal to b and cross section has a form of small square of side A. Okay, the solenoid winding consists of total n turns. So this is what has been shown to you. So this is a toroid with a cross section of A by A square. Okay, so this is A and this is A. So the cross section of the toroid is a square of side A. The inner radius of the toroid is of radius B, and the outer radius obviously would be B plus A. So you have to find the formula for inductance of this toroid. Okay, so try and find the answer for this. Okay, I hope you remember the formula for the magnetic field due to a toroid. There are two ways. Usually we can ignore the variation. You can consider that A is very small compared to B. Okay, that can be done. But suppose if that is not to be ignored, then what will be the answer? Let's try and calculate the answer first without assuming that A is too small. Okay, and then we will take a look at that special case also. If A is too small compared to B, then what the result will be. So I'll give you guys 1 minute to give this problem a try. Okay. Let's see. So what did I tell you? How do you calculate the self-inductance? So assume some current I flowing in this. Try and calculate the total flux linked with the toroid due to its own magnetic field, and that is how you would have done that. Okay, Mr. Ankit Kaushik. So, what do you think is happening here? Hmm. ये कैलकुलेट करके दिखा दो भाई फिर एंड फिर देखते हैं ठीक है अगर पढ़ना वढ़ना नहीं है यू डोंट नीड टू कम टू दिस चैनल ओके यहाँ ऐसे भी सबके लिए है नहीं ये सबके बस की बात नहीं है इतना पढ़ना इफ यू नॉट सीरियस देन यू कैन गो एल्सवेयर ओके the rest of you guys can try this And let's see if you can solve this. I already told you how you would go about it. Okay, let's see. So is anybody trying this? And if you don't know how to go about this, if you can't solve this, then also don't worry. I will just show you the solution. Okay. All right. So what essentially you will do is, first of all, since I told you to ignore the assumption, do not consider the assumption that A is very very small. So what you need to do is you will first need to consider a small portion at a distance r of thickness dr like this. Okay, so imagine this small segment which has a thickness of dr. So imagine a circular ring like this. Okay, so imagine a circular ring like this going through the whole toroid. Okay, so this is at a radius r and has a thickness of dr. Okay, now what will be the magnetic field at this point? What will be the magnetic field at a distance r from the axis of the toroid? Let's try and write that. So magnetic field at any distance, I already know B is naught times small n I, where small n is the total number of turns per unit length. So here for the section shown will be n, small n would be total number of turns over 2 pi r. Correct? The total length of that strip would be 2 pi times small r. So this would be the n. Okay. So you will realize that B is mu naught times n times I over 2 pi r. Right. So what is the flux linked with this small strip? So this strip is you can realize it's a cylinder. It's a cylinder kind of. It's a ring kind of thing. Ring kind of thing of radius r and thickness dr. Okay. So how much would be the flux linked with it? D phi you should know would be n times B times dA. Right? Where dA is the area of cross section. What is the area of cross section? Area of cross section you will realize is dr is this thickness, A is this length. So every cross section of the strip would appear like a rectangle where this side would be dr and this obviously is A. So the area of cross section is A times dr. Right? So your d phi turns out becomes capital N times mu naught n I over 2 pi small r times A times dr. Okay. Now, if you can integrate this, then you will find the total flux, right? So let's integrate this to find the total flux. So when I integrate this, everything else is a constant and only r is the variable, right? And the limits of r would have gone from b to b plus a. Right? This is how you would have gotten this. So you will realize that phi would be equal to mu naught times capital N square over I over 2 pi times a into ln of b plus a over. Okay. Now, since you know the phi, you will realize that inductance would be phi over I, which is nothing but mu naught n square a over 2 pi times ln b plus a over a. Okay, so this is how you would have done it. All right. Now you could have done this under an assumption also. If you take the assumption that A is very small, then you can almost consider the B to be uniform. Okay, and if you consider B to be uniform, so if your A was so if A was much less than B, then consider B to be uniform, which would have been mu naught times capital N over 2 pi B then. B would have been the average radius only. So this would have been the B, and for calculating the flux, I would have simply multiplied this by A square. So this is another way of calculating this. If I assume that A is much less than B, okay, then what you realize is that phi will become mu naught times n square I over 2 pi p times square. And now also you could have calculated an approximate answer. Okay. Approximate answer would have been now in this case mu naught n square A square over 2 pi b. Okay. This is your answer without any approximations. All right. So now let's talk about the growth of current in an inductive circuit. So what will happen if you connect an inductor to a battery? I want to see what will happen. So at any time, let's say if the current I is going like this, okay. So if I write KVL KCL equations, so I can write KVL equation. KVL equation would tell me if I start from here and if I go from here to here, then the delta V would be plus E, where E is the EMF of the battery. And let's assume that this inductor has an inductance of L. So across this, always remember, whenever you're moving in the direction of the current, whenever you are crossing an inductor in the direction of the current, delta V is always minus dl by minus L di by dt. So why so? Because this is an ideal inductor that we are trying to study. So ideal inductors don't have resistance. So only potential difference across them would be due to the back EMF. Okay. So that will be minus L di over dt. So writing the Kirchhoff equations, what we will get is, so writing KVL equation, we can see that plus E minus L di by dt would be equal to 0. Okay. So also I will write that di would be equal to E by L times dt. So you realize you're getting a very interesting result. So initially, if the current was 0 at t equals 0 and at some time t, the current is I, then what you realize is that I equals E over L times t. So how is the current going? Current is going linearly. Okay. So in a purely inductive circuit, the current does not immediately go up to infinity. So if instead of inductor, if this is a straight wire, then immediately the current would have become infinite. So here does the current become infinite? Yes. At t equals infinity, it does. However, the graph of variation of current with respect to time would be like this. So if you had I on this axis and time on this axis, you would have seen that this is how the current would have grown. And the slope is inversely proportional to the inductance. So higher the inductance, slower would be the growth in the current. What all can you realize from here? What all can you realize from here? This will always have a finite slope. Okay. This kind of graph will always have a finite slope, which means that a di by dt is always finite. Okay. So from the graph, what we realize is you can see that the current, you can notice that the current in an inductor can never change instantaneously. That is a property of an inductor. Imagine to increase the current, across the inductor, you would have had to apply some EMF, or you would have had to increase the voltage across the inductor. So if the current could change instantaneously, then a back EMF would have gotten induced, which was equal to L di by dt. Now di by dt for an instantaneous change in current would have been infinite. So you realize to actually change the direction, the amount of current flowing in the forward direction significantly, you would actually require a forward EMF also, which will be infinite, so that it can overcome the back EMF, infinite back EMF, right? So which obviously is impossible. So what you can conclude is that the current in an inductor can never change instantaneously. You notice that the current through the inductor never changes instantaneously. Okay, so that's the first thing you can notice. What are the other two things that you can notice at t equals zero? At t equals zero, just when the switch is key is switched on, then you will notice that the inductor will behave as an infinite resistance. Okay, because the current would be zero. So this is my second observation. At t equals zero, the inductor behaves as an infinite resistance. Right? How about at t equals infinity? At t equals infinity, the current can actually grow up to infinity, right? There can be infinite current, which is fine because resistance of the circuit was actually zero. So as the current slowly and steadily grows, you will realize that it can reach up to infinity. So at t equals infinity, how is the inductor behaving? The inductor behaves like a resistorless wire. Does this remind you of something? Do you remember how a capacitor would behave? A capacitor, just when you would have switched on its charging circuit, would have instantly allowed infinite current, and the moment it would have become charged, it would have suddenly behaved as an infinite resistance. Okay, so I hope you remember from your capacitor studies. All right, Amol, good to know. Now, let's also talk about the energy stored in the inductor. So we kept saying that it is a device which is storing energy, just like capacitor stores energy in electric fields, and inductor is storing energy in form of magnetic fields. So how much is the energy stored in an inductor? So how do I calculate that? So let's see. How am I, or who is doing the work to store the energy? It is the battery that is doing work, right? So here you can see that when the current was growing, the source that was responsible for increasing that current was the battery, right? The battery is pushing that current and causing it to grow. So you realize whatever work is being done to push the current or increase the current across this, that would be that would be getting stored in the inductor in form of energy, right? So let's assume that at any point, if at an instant if t, the current in the circuit was I, and it was changing at a rate of di by dt. Let's assume that. So you realize at this instant that the back EMF would have been minus L di by dt. So this would be the voltage which would oppose the flow of current. So to flow the current, right now the battery would have had to do work against this back EMF. Okay, so I can write to flow an additional charge dq, work will need to be done against the back EMF, right? So how much work will be needed? So you are transferring a charge dq across a potential difference of L di by dt. So you will realize dw would be L di by dt. This is the work done by the external agent into dq. Okay, this is the work which the external agent would do to flow the current through this. Okay, agreed. Now you will realize that this dq by dt would be nothing but I, right? So can I say that dwe is L I I. Now for finding the total work, you will integrate this expression and the current goes from 0 to some I, which will tell you that work done by external agent is 1 by 2 Li square. This is the work. And where is this work going? Where is this work going? This is the work that is getting stored in form of the electric energy stored in this magnetic field. Okay, so you realize you are creating magnetic fields here. I told you in current electricity, when you create electric fields carry energy. So if you're creating electric fields, you have created something which has energy bound to it, right? So to create such a thing, obviously energy would be required. Okay, because of energy conservation. Where is that energy that is stored in the electric field coming from? Somebody must have worked in creating electric fields. Similarly, magnetic fields also carry energy. So when you're creating magnetic fields, you will need to do some work, and this work, which goes into creating those magnetic fields, is getting stored in form of energy of that magnetic field. Okay? So if when the current I is flowing at any instant, when the current I is flowing, in an inductor, then at that instant, the energy stored in the inductor is half Li square. Okay, and this is the derivation. I hope there is no doubt about this. If you did not follow this, then you can let me know. But this is very simple. All I needed to do was I calculated what will be the work that the external agent would have to do in moving a charge from this end to this end. So if I'm moving a dq from here to here, I know that the potential difference back EMF that is getting induced, or I can say that the inductor is opposing this with a potential difference of LDI by dt. So external agent, if it can do the work against LDI by dt, then it can transfer that charge dq from one end to another. Okay, so in transferring that charge, the work done by the back EMF would happen delta V times Q. I hope everybody remembers this. That work done was delta V times Q. So the external agent must have done an equal amount of work. Okay. So this is how you get the expression for the energy stored in an inductor. Now we will try and calculate the energy density in magnetic fields. So I already know if I consider the solenoid to be infinite, then I can ignore the magnetic field outside, right? So this magnetic field can be roughly ignored. I can assume that all the magnetic field is almost lying inside the solenoid only. All the magnetic field lines are almost lying inside. If the size becomes infinite, then that is a very, very valid assumption. Okay, so we will start with that assumption. So, assuming the solenoid to be very long, why very long? So that I can make all the assumptions of an infinite solenoid. Okay, so all magnetic field lines lie inside. Right. So what is the energy stored here? Energy stored U was half L times square. Okay. Now I hope you remember we had talked about the inductance per unit volume. So inductance per unit volume for a solenoid was mu naught n square. So obviously L is mu naught n square times V, where V is the volume. Okay, I hope you remember we had just discussed that a while ago. Correct. So I'm going to replace that in this expression of my internal energy. It will be half into mu naught n square I square times V. Right. Now all I need to do is multiply and divide this with naught and you know. Now what you will realize is that Q becomes 1 by 2 mu naught Ni whole square over mu naught times V. So from here, what I can see is that U is the energy density would be U over V. U over V is nothing but half. And what is mu naught? Mu naught Ni. Mu naught Ni is the magnetic field strength, right? Half V square over mu naught. So this is the energy density of magnetic field. So anywhere, if you have a magnetic field B, then it stores the energy of 1 by 2 B square over mu naught as energy per unit volume. I hope you can remember the analog for electric fields. Let me remind you. For electric fields, what was du over dv? Du over dv is half epsilon naught E square. So you realize there is a similarity in the equations also. So energy per unit volume in magnetic fields is half of B square over mu naught. Okay, very similar results. So again, must remember, very important. Again, we have derived this expression from an inductor, but turns out this holds true in anywhere. So why? Obviously, with the nature of magnetic fields, this energy is stored in magnetic fields. So magnetic fields do not care, no, where they are getting originated from. So important result must remember. Okay. All right. So I hope everybody followed this derivation, how we calculated the energy density of a magnetic field. Okay. So if you followed this, then let me know. We will move ahead. Okay. Now here I have one question for you to practice. I have just two questions for you to practice. I knew this was a short session. Okay, because of the quiz day, we have slightly shortish sessions. So here is a quick question for you. The current in a coil of self-inductance 2 Henry is increasing in accordance to the expression I equals to sine t square ampere. To find the energy spent during the time period when the current changes from 0 to 2 amperes. So how much energy is spent by the source in the time in which the current grows from 0 ampere to 2 ampere? No, very tough. Not at all, AP. This is like one of the simplest problems. Okay, it just appears tough. All you need to do is remember where will this energy go. So this energy spent, where will this go? Okay, if you remember that, if you remember the formula of that, you just discuss it. It would be very simple. So okay, why don't I show you maybe? So I can say that energy spent would be equal to energy stored in the inductor. Okay. Oh, by the way, here you will notice something very different from your capacitor charging circuits. So in capacitor charging circuits, if the energy stored was half CV square, and then the actual work done by the battery was CV, right? CV square, and half of it was disappearing somewhere. In case of inductors, all the work done by the battery gets stored in the inductor only. Nothing gets disappeared. At least in an ideal circuit. Okay. In capacitors, we realized even in ideal circuits, half the energy was disappearing. That is not the case with inductors. All the energy spent by the source gets stored in the inductor itself, and that is how I know this would be half L square. This is the final energy. Initially, it was 0. Okay, so half into inductance is 2, and current has to become 2. So 4 joules. That's it. As simple as that. Okay. All right, let's try just one more problem and then I will wrap up today's session. So uh, in this question, you've been asked what inductance would be needed to store 1 kilowatt hour of energy in a coil carrying 200 ampere current. You have to find the inductance of the coil which can store energy of 1 kilowatt hour. So pay attention to the units by carrying a current of 200 amperes. Try and answer this very quick. So this is very simple. So I'll probably give you 1 minute to answer this. Just pay attention to the unit and you should be fine. Okay. So anybody solving this? No. All right. Let me quickly show you. How much energy is 1 kilowatt hour? So 1 kilowatt hour. I don't know if you remember this was 3.6 million joules. Okay. If you don't remember this, derive it. Okay. I am not going to show you. You should be able to derive this. Okay. And I know energy stored after. How much is that? That is half Li square. So I want my half Li square to be equal to 3.6 million joules, right? Therefore, 1 by 2 into L into I square, which is 200 whole square, should be equal to 3.6 into 10 to the power of 6. So what you will realize is that this would become L times P. So okay, so let's get rid of 10 to the power 4 from here and let's write it as 360 over 2. Okay, that is what you will have left. Okay, you can calculate this quickly. There is 10 to the power 4, which will get cancelled. Oh, okay. So this will get cancelled, and here you will have 10 to the power 2. 1, 2 will also get cancelled with this 2 square. This is what you will have. This is 180 Henry. That is your answer. Okay. So this is where I would like to wrap up today's session and today's discussion about inductance and self-inductance and inductors. In the next class, we will carry forward this discussion and we will talk about LR circuits. Okay, and that is an important part. Trust me, in AC, you will analyze a lot of LR circuits, RC circuits, LC circuits. So make sure you attend that lecture live. All right. So before I leave you, let me remind you one last time that if you haven't gotten your Unacademy subscriptions, you should be getting them, and this is how you do it. You go to the plus section of your app, you select your goal as IIT JEE, and you click on that get subscription button. All right. So once you click on that get subscription button, you will be redirected to the payment page where there will be a box saying, "Do you have a code?" That is where you can use this code. RD Life is my code. This code will help you get a 10% off on all his subscription fees. And then you can simply click on proceed to pay, select a payment option which suits you and get your subscription. And when you get your subscription, this is what you can do with it right now. So there are three courses which are ongoing on class for class 11 students or 2022 aspirants. You join these courses. These are all being hosted by the JEE English team. Then you have four more courses which are being hosted for class 12 topics or 2021 aspirants. So you can quickly join. All right. Now, if you like today's video, then don't forget to press that like button and share it with as many friends as possible. As I keep saying, that those of you who can't afford that uncapped subscription can keep following us on the JEE English channel. We will try and give you as much quality content here as possible. So maybe not personal practice, but theory wise, we are covering the theory very extensively. I am covering everything from basics to the advanced level here. So trust me, this will really help you from your boards to your JEE Advanced everywhere. So this is quality content completely free of cost provided to you by Unacademy. So make sure that you are sharing this video so that more and more students can benefit out of this. Okay. Don't forget to press the bell icon and the PDF notes of all the slides used in today's lecture would be available for download very soon. All right. One more time, if you want, you can. In fact, you should be a part of the Unacademy Combat, which is going to be live on the 22nd of November. So this is going to be a fun version of IIT JEE battle. And if you do well, you also win rewards and prizes. Okay, you can enroll now with this code RD Live. Okay, and good luck and win some prizes. Okay. Next, if you're following us on the JEE English channel of YouTube, you don't forget to connect with us on the Telegram app using this link. Okay. Finally, before I leave you, one last time, let me remind you that RD Live is my course. So if you like my lectures, if you would like to enroll in my courses on the Unacademy Plus, if you want me to be your personal guide for your IIT JEE journey, then you can use this code to get a 10% off on your next Academy subscription. All right, so with that, I will take your leave for the day. We will carry forward with this discussion day after tomorrow. So I will see you then. Till then, you guys keep studying hard, keep practicing, and take care.